Again, welcome to Griffith Observatory. My name is Laura Danley. I'm the curator here. Oh, well, yay, I have a job. So thank you and welcome. I've got low feedback here. First, I just want to ask, how many of you are members of the Cassini team, are scientists with Cassini? So look around, we've got a lot of scientists here, and I think if there's anybody who deserves a round of applause, it's the science team. How many of you are regulars for All Space Considered, our Friday night program? Oh, we love you so much. Thank you for coming back. How many of you are photo members? And we really love you, so if you want to be really loved, join Friends of the Observatory, which is our membership organization, which also helps underwrite so many of our expenses for our program, our school program for all the little children. How can you resist? We hope that you will consider becoming a photo member.
How about a round of applause for the taxpayers? You make an excellent point, because maybe some of you don't know, this is run by the City of Los Angeles Department of Recreation and Parks. And, not a lot of cities have a free, beautiful observatory like Griffith Observatory to come to. So thank you, taxpayers. Thank you, Photo. Thank you, Cassini team. And the rest of you, well, we're glad you're here too. So anyway, I've already taken up many minutes in the introduction that I really should just jump right to the program, because we have such an exciting program tonight. It made me so sad to limit the panel to just, a few minutes each to go through, because frankly, we could have a whole evening with each and every one of these individuals and still be wanting more. There's just been so much excitement and wonderful science coming from the Cassini mission. So tonight we're going to get just to hear a little bit of an overview. They happen to be having their science team meeting at JPL, and they came over here for dinner and a lovely sunset. And so we're so happy to have them here. I want to make a few kind of housekeeping announcements and then introduce our panel, and then get out of the way so you can hear about the Cassini mission. First announcement is, if you have a cell phone, turn it off. The second is, if you must leave during the program, please exit out the back. I know this says exit, and it is an exit, but it really is only for emergencies, because it goes to this crazy little place back here that you will get lost and scared. So if we have an emergency, we will lead you out, but if you need to leave, back doors are your exit. Let me also say that we had a harpist. One of the Cassini team members plays the harp, and she played on the West Terrace today. So if you're in here, Janet, we thank you. It was lovely. And so this is not part of this evening's program, but we didn't want to leave it up on the terrace. So here it is, if you're wondering why there's a harp. And lastly, this is being videotaped and will probably be streamed on the Cassini team Facebook site. So if you don't want your face to be seen, just do this when the camera comes by. But you may, by coming in here, you've consented to be taped and possibly broadcast or webcast on the web. So just let you know that. We're trying to make sure that your consent is all right. So I think I am ready to move with the introductions, and so if I can ask our panel to come up and have a seat. This is my chair, so you can take those 5, and I will start with the introductions. And this is so embarrassing, because they'll have to all look at their pictures, because I got them off the web. Our first panelist is Kevin Baines, who is at Jet Propulsion Laboratory and has been there since 1984, first as a research scientist and now as a principal scientist. He's worked on many different missions, Venus Express, Galileo, and he's the Venus, Earth, Jupiter Atmospheric Science Coordinator. I thought that would sound like such an intriguing title. He's now, of course, with the Cassini mission. He's going to be telling us all about the actual planet. We can't forget about Saturn with all the, we're saying, oh, those rings and moons, they get all the glory, but Saturn is the real, has all the gravitas, as we said, and is the real show in town. So he's going to be telling us about that. He got his PhD in physics from Washington University. Linda Spilker is our next speaker, and she's the deputy project scientist for Cassini. She's been with the mission since 1980? No, is that my handwriting? 1990? I can't read my own writing. 1990. 80, that is my own. Wow. and is before that worked on Voyager and as both in infrared and also photopolarimetry. And she got her PhD from right here in Southern California, UCLA. We're happy to have her here. She's here to talk about the rings. Maybe some of you have seen her on TV. I've seen her. She's done a lovely job. Thomas Gombosi, who is the magnetosphere scientist. He is the Roland Gerstacker Professor of Engineering at University of Michigan and the chairman of the Atmospheric, Oceanic, and Space Sciences Department. He's the director of the Center for Space Environment Modeling, and I understand, just learned, has been working with other planetariums to do some beautiful visualizations for planetarium shows. He's Hungarian by birth and actually worked with the, I want to say Venera as opposed to Venera, but I actually don't know the proper pronunciation. Venera?
Venera.
There you go. Which, as some of you may remember, is the Soviet Union's missions in the mid-70s to Venus, actually landed on Venus. And so he's been doing a lot of space research for a long time. He's a member of the International Academy of Astronautics, fellow of the American Geophysical Union, been an editor on many different scientific journals and a long list of awards and service. And we're just thrilled to have him here. He's going to be talking about Jupiter's magnetosphere. Jupiter, Saturn, you know, they're all one of those gassy planets out there. Then next is Amanda Hendricks, who is also at JPL and has been there since, or been part of the Cassini team since 1999, if I'm correct. And has got her PhD from the University of Colorado and was a postdoc there as well. She's also involved in many future, oh gosh, I skipped over everybody's future involvements. Everybody's involved in new projects after Cassini, so I'm going to have to just skip that since I didn't do it for everyone. But she is a co-investigator with the ultraviolet imaging system and the Galileo ultraviolet spectrometer experiment on Galileo. She's going to, oh my heavens, I've forgotten what you're talking about.
Satellites.
Satellites, good Lord, how could I forget? Yes, those moons, I've blocked them out. I shouldn't say that. The satellites that have been getting so much wonderful press, very exciting. And lastly, Jonathan Lunine, who is professor of planetary science and physics at the University of Arizona, is a distinguished visiting scientist at NASA Jet Propulsion Laboratory, where he's a member of the Directors Advisory Council. He's an interdisciplinary science on the Cassini mission to Saturn and an interdisciplinary scientist for the James Webb Telescope, which is the Hubble Telescope follow-on. He's also involved with the Juno mission concept under development. And he got his PhD also here in Southern California at Caltech, and he's an author of many popular books and fellow of the American Geophysical Union. And again, the list of honors and awards and chairmanships and service goes on. So we have an incredibly distinguished panel here today. About 12 years ago, the Cassini satellite was launched to Saturn, not Jupiter, but Saturn. And in 2004, 7 years later, it went into orbit. And I just will say, on a personal note, I remember that happening because there was a prediction of when Cassini should go into orbit, and I think it went into orbit within less than 10 seconds, like 3 seconds of the predicted time. The engineering was so right on that it gives us some kind of sense that in fact we know what we're doing and we know what we're talking about, and science is a very productive way to understand the universe and interact with it. So it's been there since 2004 and has now moved into its extended mission, and the Equinox mission as they call it. I'm sure we'll hear a little bit more about that. And I think that is really all I'll say by way of introduction, so that we can bring everybody up to the same level. We're so glad you're here, and with that, I think I will turn this over to you, Kevin, and thank you very much. And let me do this. You and the audience have to watch our changeover procedures. There you are.
Well, great. Well, thanks a lot for having us here. Really appreciate this. It's my first time back at in this area since it was redesigned, I guess, and rebuilt. It's really beautiful here. I got a lot to talk about. We've done a lot of things at Saturn. Since being there for 4 years now, and it's no longer your father's Saturn. It's a whole new Saturn we're looking at, and I'm going to show you why it is. Now, this is a typical picture of Saturn here that you've seen from Voyager and other types of imagers. What we've done on this mission is we've got a number of new instruments that see in different wavelength ranges. So you can see Saturn in a whole new light, and reveals the depths of Saturn, as well as things really high up like Aurora, better than before. So I'll show you that. Here's a little tutorial really quick on Jupiter, Saturn, Uranus, Neptune. Those are the largest planets out there. Sort of the gas giants, mostly comprised of hydrogen and helium, which are the most abundant materials in the universe. So you expect them to be the most abundant things in the biggest planets, and indeed they are. And there's Saturn, just sort of a little brother of Jupiter, but almost the same size. But then down below you've got Earth. So if you want to do things to scale, there's little Earth, and there's Saturn and Jupiter. So those are really the lords of the solar system. And but all along, Jupiter's gotten most of the credit for being a dynamic place. We've got the red spot here, in lots of storm systems on Jupiter. Here's poor Saturn, not for kind of boring looking. Here it is here too, in a more recent image in the visible, which looks not too exciting. And here's a picture taken a couple years ago with the visible camera, and shortly, within a few seconds of this picture being taken, we took another picture in the near-infrared, and this is what we saw. So you see a whole different perspective to the planet, lots of features up here, which I'll explain in a second, and you see a variability between this hemisphere, northern hemisphere, and the southern hemisphere. Shows you a lot of hemispherical and seasonal things going on. But all these features in here are really deep in the atmosphere. Most of those have never been seen before. So I'll show you highlights of that really quick as we can go along here. Just to kind of explain what's going on. Red here is at a wavelength of 5 microns. That's about 8 times the wavelength you can see. So it's really where heat is. So you're looking at the thermal heat of the planet. This planet is so deep that if you go down into the atmosphere, it warms up just like when you come down from a mountain or come down from an airplane on the surface of the Earth. It gets hotter and hotter and hotter as you go down to the surface. If you go down into Saturn deep enough, it gets to be room temperature, and then it gets to be even hotter, and it can get up to several thousand degrees. So there's a glow to the planet, and this is being blocked. This glow is being blocked by these clouds. So here, the black smudges are clouds in silhouette, basically. And these clouds have big particles in them, bigger than the particles we see up above, up here. And so we're seeing a whole different regime of the planet with this device at 5 microns. It's called the VIMS Instrument Visual Infrared Mapping Spectrometer. So this has allowed us to see deep in the atmosphere. Here's sunlight here. You can see that the sun's coming from over here. And you see very high. Back here you see it's night, so you don't see it. But the glow still works. So the red aspect of it still comes through day or night. So this technique, which allows us to see deep in the atmosphere, allows us to see both day and night at any time. So it's kind of cool thing to do. So explain that. Here's some features. Now here's a typical visual view, typical type of high clouds here that we're seeing. Here's the ring, by the way. It's the rings, as atmosphere scientists like to see rings, edge on, so you can see. And here we have the high clouds. And now the revelation of 5 microns, thermal flux, these little black clouds here are blocking the light. These features are very unique. We haven't seen those before. And is there a connection between here and here? We think there are. We're calling these plumes. We think those are updrafts. And to collaborate that, we've also got radar images. We've got this radar, which we never had before. And we don't use radar as the usual standard. We sort of just keep the radar off. We don't ping anything. We just let it sit there passively. And we're looking at the 2 centimeter radiations, about 1 inch long radiation coming out of the planet. And it so happens that ammonia gas absorbs that radiation. So if you see any variability, like you do along here, that means there's different amount of ammonia gases in the atmosphere. So we're seeing ammonia gas bubbles here coming on up in the atmosphere, and they have the same size and the same shape as the clouds I just showed you, the plumes. So we think we've got this unique thing where we've got bubbles and plumes coming up, showing dramatic upwelling in the equatorial region of Saturn, and that then probably gives you these clouds that we've always been wondering, why is there more clouds in the equator? Well, it's probably due to that. Now here's a quick tour of Saturn. Indiana Jones meets Saturn. The second you're going to understand why we say this. This is not your normal Saturn. This is a much more ominous looking Saturn than you expect. And we'll see if we get this thing to work. There it is. I'll talk about it. So Saturn is no longer boring in my point of view. Okay, here's the hexagon going through like an axle of a wheel. And then beyond it, you got the string of pearls going on along here. This is a feature you haven't probably heard much about, but there's these 24 lights that are in the atmosphere that have been there now for 4 years. We just saw them again. First time we've had a chance to look at Saturn was a week ago, and just driving over here, my postdoc called me and said, guess what, we still got the pearls. So now we've got over 4 years of pearls data there, and we don't know what they are. These are, so I'll explain in a second if I get time. but it's very bizarre features. So we have that. We also have donuts. Here's a donut going by. I say a donut in the atmosphere. But anyway, a lot of neat things. So we're going to keep going here. Here's the pearls. Okay, so you got lots of pearls here, but it only covers about a quarter of the planet, so it can't quite be a total planetary wave because it doesn't go all the way around. So, but they've been there for 4 years. We have no idea. So this number here is now 4.2, not 2.8. And just to show you that they've been there all the way through the mission every time we've looked. Here's the donut that I just explained before. Call it a donut because this is actually, again, you're looking at thermal light, so that's a clearing, and then this circular black thing is a cloud. So it's really like a donut or Taurus, Toretto cloud. They're up around 53 degrees north latitude. Here's the hexagon that we got a first clear view of. We knew about it from Voyager, but this is a mission because we go up over the pole, we can look down, so we get a very clear view of it. And here it is. Here's the sun rising. Over here's the sun rising. This has been in darkness until recently. The equinox just happened, so now it is getting lit up. But up until just recently, it was in total darkness. Lots of explanations for this thing coming out of the woodwork. This is the best explanation we have so far. We're still looking, trying to come up with the real explanation. This was in the paper. I cut it out, so this is fantastic. Anyway, so now we've got this view. Here's the actual pole, and you can see these. Now we're looking at the winds around the hexagon. But look at in here at the cyclone. There's a cyclone feature. You see winds blowing very fast. These little cloud features are going very fast here. But look out here. These cloud features don't move at all. So you have this sort of whirlpool effect, and there's a cyclone at the pole that we didn't know about. We've now documented it, and there's, you can see it visually right there, a little whirlpool at the North Pole. I'm going to skip over this. By the way, that was a hurricane on the Earth compared to that. Okay, now the South Pole also has a cyclone, and it's much more hurricane-like in the sense that you have different depths, and this is showing 3 different colors for different levels in the atmosphere. Red means it's deep, green means it's a little bit higher up, and blue means it's high. And you can see in the eye of this, it's a deep atmosphere, much like a hurricane feature on the Earth, although the scale here is tremendously different than hurricanes on Earth. But it seems to have a hurricane-like feature. And in fact, if you look from the side and you get close like the ISS people, this is the camera people can do, they actually see shadows. So here you can see these clouds are much higher than the clouds. They're casting shadows on the lower clouds. And you get this 3D effect. It's really real. You're actually seeing the clouds in 3 dimensions. They're so high up, they're about 70 kilometers above the rest of the atmosphere there. So we have this unique cyclone at the South Pole. It looks a lot like a hurricane. And then we have the thunderstorms. And here's some thunderstorms that we're seeing in this thunderstorm alley area about 35 degrees south. It turns out the southern hemisphere doesn't have all these features I've been talking about. The northern hemisphere, donuts and pearls. But it does have thunderstorm alley. And we've been seeing discharges in the radio signals, like using your AM radio. And we've been seeing discharges off of the mission, almost most of the time to the mission, of lightning, but you can't see the lightning visually. Nobody's seen it visually. However, you see strange things when you go take images. And here's a strange thing, dark clouds. Okay, dark clouds here and a bright cloud here. This bright cloud is made up of ammonia now. We've confirmed that. And the dark cloud here is dark throughout the whole spectrum. So what is dark throughout the whole spectrum? You might think of charcoal, and that's indeed what we think it is. The paper just got published on this. So we think we've got dark charcoal-like stuff upwelling, as this diagram shows. So we think there's a layer of soot here, which is coming on up, and the ammonia cloud comes out first as you updraft these things. The wind up here kind of blows the ammonia cloud around, but beyond the ammonia cloud, beneath it upwells a few days later this sort of dark material which is embedded in the ice, and we think now there's probably a little charcoal-like substance soot sitting down there all the time in the depths of Saturn around the 10 bar level, very far down, on this scale here, about 200 kilometers down from the 1 bar level, and periodically when you have these huge updrafts with thunderstorms powered by water, same stuff as on the Earth, that release of energy brings this stuff up, and we think we get these black spots. So that's a very recent finding. Okay, last thing, I'm going through this pretty quick. This is good. Last thing is aurora. Okay, so we have these aurora, which can be done by several different instruments. We have northern lights basically on Saturn, and here it is with the UV, so ultraviolet lights, CH. And then we see H3 plus, which is a chemical that's involved in the actually formation of aerosols too. Out of this comes aerosols, just like on Jupiter. And we're starting now to document this. It's a little bit of effort for our camera to actually get these types of observations. But here you have an aurora right over the hexagon. I don't think it's a coincidence, but a lot of people are thinking. I think it's a coincidence, but a lot of people are thinking maybe there's some cause and effect. We don't think so. This thing's way up high at microbar levels, whereas the hexagon is down at 1 to 2 or 3 bars. It's down there, so I don't think there's any real effect. It's just a coincidence here that you get the aurora hanging around this. But it's a very beautiful picture here of the cyclone at the pole and the hexagon, and then the aurora above it, lingering there. So I'll just leave you this famous picture. I think everybody's seen this. I think I saw it on the train when I came in, of a unique view of Saturn. This is Saturn right here with the sun behind it, so it's an eclipse, and you see the rings shimmering in the sunlight. And if you haven't seen it, over here is actually us right there. And if you blow it up, you can wave at yourself. There we are, 1 billion miles away. This is a picture taken from 1 billion miles away, seeing the Earth basically shimmering through the rings of Saturn in eclipse. So that's probably this is the iconic picture, I think, of the mission so far. So I had to end with it. Okay, that's it. Thanks.
Kevin, and there will be opportunity to ask questions. The reason I'm asking all the speakers to Zoom through is so that we can have a really nice long Q&A section after this. So thank you, and Linda, you're up.
Well, thank you. I titled this talk Saturn's Magnificent Rings because I really think that Saturn has a great ring system. You know, Kevin showed you the outer gas giant planets. All of them have ring systems. But without a doubt, the Saturn ring system is the most extensive and I think in many ways the most beautiful. The rings have very simple names. They're just the letters of the alphabet. And we've gotten a little bit more creative with Cassini as we've discovered new rings. We tend to, if they're affiliated with moons, then name them after the moons. But here, if you look through a telescope, the main rings that you would see would be A, B, C, D, and perhaps even with a good telescope, a chance to see the Cassini division. There are other rings at Saturn as well. There's a very narrow F ring. You can just see it in this image here, just outside the edge of the A ring. We've got the G ring, very extensive E ring. We've also, over the course of the Cassini mission, discovered a host of tiny new moons, like Pauline that has a ring associated with it, or Anthe. And one thing I heard that's kind of interesting, when we were discovering these tiny moons, they often seem to have rings. And one analogy might be when you see a dog often has fleas. So if you think of the tiny moons like a dog, then you've got these little fleas that they kind of scatter around the Saturn system. For scale, the Saturn plus its rings is really a huge system. This shows Saturn, the Earth, and the Moon to scale, and the distance between them is to scale as well. And you can see that you can just neatly fit Saturn plus the rings in between the Earth and the Moon. And the rings are made primarily of water ice, and as we've learned with Cassini, those water ice particles tend to clump into clumpy structures, especially in the A and the B rings. They range in size in the main rings from marble sizes up to large houses and even mountain-sized particles. And so one of the neat new discoveries with Cassini is the fact that these particles tend to clump up. Now if you go back in history before Voyager, before Cassini, there was another very interesting idea about what Saturn's rings might be made of. And so if you ever wonder where your suitcase goes if it doesn't come off the belt at LAX, now you know they might be part of Saturn's rings. This is a movie of the rings. It's starting on the lit side. You can see the A ring, Cassini division, and B ring. And let's see if we can get it to play here. There it goes, and this is pictures taken by the Cassini spacecraft as we're flying, as we're trying to fly through the rings edge on, and you'll go through, see them edge on. I guess it's not going to work. Give it one more shot. Okay, well, as you go through, what you'll see is what you would have seen is this optically thick B ring becomes very dark. There's a little bit of material here in the Cassini division, and that brightens up. And it's really kind of fun just to ride along with the Cassini spacecraft and watch as we go by the rings. Now, the big event was the equinox, and so I'm going to spend some time. You saw some of these images if you were here for the virtual singers. This is a mosaic of 75 frames put together through a series of filters so we can have a color image. And this is what Saturn and the ring system looks like with the sun just edge on to the rings. Now this event occurs only once every 15 years, and we were very lucky to have the Cassini spacecraft there. We were in an orbit inclined about 20 degrees to be able to look at the rings, because when the rings are edge on with respect to the sun, they're essentially edge on with respect to the Earth as well. And so it's very difficult to observe the rings. So we got a whole brand new data set. And just this August 11th was equinox. In this series of frames, we've had to brighten up the rings by about a factor of 20. If we didn't do that, they'd basically be invisible when compared to the light from the planet. We've also had to brighten up the darker region of the rings as well. What you're seeing now is the rings essentially illuminated by Saturn shine. It's as though you've essentially turned off the sunlight, and you get to see what the rings look like just in the light coming from the planet. And as you can see going back here, what's brightest edge on is the F ring. That the F ring remains bright throughout the equinox time. It's at the edge of the rings. Just want to show you some highlights. When you can look at the rings edge on, what it does is it gives you a chance to look at the three-dimensional structure in the rings. And anything that sticks up above or below that plane of the rings, which is only about, we're thinking on the order of maybe 10 or to 30 feet thick. It's not very thick compared to its extent. Anything that sticks up above and below is going to be bright. In particular, there's a gap here, the Yankee gap, a tiny moonlit pan orbits inside of it. And you can see these bright ringlets have clumped up, are actually sticking up above, or in the case of the darker regions, perhaps below the rings. And we can see the clumpiness by looking, the sunlight's coming from this direction. Another tiny gap, the Yankee gap, has a tiny moon named Daphnis. Daphnis's orbit is slightly tilted with respect to the rings, and it pulls the ring material out of the plane. You also see other places. Here's a bending wave, a place where material is lifted above and below the ring plane, and not only is it bright, but it casts a shadow. So you can see a shadow, and there are other bright features in this view as well. Just want to zoom in on this area with Daphnis. What you can see here, this is an enhanced image, but you can see the shadow and this structure that's coming up perhaps as much as 8 miles above the ring plane, in this very narrow ring plane. Just want to briefly go over some of the key objectives. We're looking forward to the next 7 years. We'd like to go from equinox to 7 years from now, go to the solstice, out to the Saturn solstice. Some of the things we want to look for are seasonal and temporal changes. How do the rings change with the seasons and as time passes? There are these very interesting finger-like dusty spokes. They're particles elevated above the rings. How do they evolve and what's happening with those? Understand more about this microscale properties and clumping in the rings. Also to understand about the time variability of these structures. How do they change with time as we look from years to decades? Some new questions. We'd like to constrain the age of the rings. There are parts of the rings that look very young, maybe only 100 million years old. And yet there are other parts, perhaps there's a renewal process going on, that perhaps the very thickest B ring might be as old as the Saturn system itself. We'd like to get more information and hopefully be able to answer that question. Also, understand a little bit better how some of the narrow gaps are cleared. Some of these, like the gap here, has a tiny moon inside it, but other gaps we've looked and looked and have yet to find any evidence for moons that are keeping these gaps open. So how are these gaps kept open? We'd like to find out. And then to determine the composition of the rings. They're mostly waterized, but there are little bits of contaminants in the rings, and it looks a little bit different depending on where you look and which ring you look through. And so we'd like a chance to study that even further. And finally, this is one of my favorite pictures. It's a unique geometry that you can only get with a spacecraft like Cassini. What we're looking at here is that we're using Saturn to basically block out the sunlight. You can see a little bit of the sunlight peeking through around the limb of the planet, and it does a nice job in particular highlighting the dusty rings. Imagine yourself driving on the freeway on an afternoon with a dusty windshield. You drive into the sun, it suddenly gets very hard to see. It's the same effect with the rings. As the sunlight shines through the rings, they brighten up, just as your windshield would brighten up if it's very dusty. And this is a unique picture also, as Kevin pointed out. In that tiny square, in that square there, is a pale blue dot. And that dot is the Earth-Moon system. And so here's one case where Cassini is looking back and taking a picture of half the people on Earth. So stay tuned. Hopefully, Cassini, their plan is to go for another 7 years and continue to return great pictures, not only of the rings, but the rest of the Saturn system. And with that, I'd like to turn over to Tomas to tell you about that invisible magnetosphere.
So far, we heard about the planet and the rings. Saturn's magnetosphere is about a few million times bigger than the planet and the rings combined together. As a matter of fact, it also implies and means that the universe, 99% of the universe is in plasma state. Plasma state means that it's ionized material. So I will be trying to talk about the magnetosphere, which is the plasma environment of Saturn. I would like to introduce the concept of a magnetosphere. So if you have a magnetic dipole, you put it into a very fast flowing flow, in this case the solar wind, which is the plasma stream, very high speed plasma stream emanating from the sun, which is supersonic, so much that the Mach number, the speed of the solar wind is about 10-20 times higher than the sound speed in the medium. So this is a supersonic, a hypersonic bullet, which is a magnet in a conducting fluid. So what happens is that the magnet has its magnetic field lines, but the streaming solar wind compresses the day side of the magnetic field and expands, stretches the night side. And the magnetosphere is basically the region of space that is dominated by the distorted planetary magnetic field and its interaction with the surrounding medium. So at Saturn, the distance from the center of the planet to the day side stand-off distance, which is around here, is about 25 planetary radii, which is huge. And on the night side, the tail goes hundreds and even thousands of planetary radii. So the total volume of the I can't turn this off. Just need that.
Here, have a different one.
Thank you. So the total volume occupied by the magnetosphere is millions of times larger than the volume of the planet. Saturn's magnetosphere basically encompasses most of the planetary satellites, and this is a very nice cartoon made by the Cassini MIMI team. MIMI is one of the particulate fields instruments on Cassini. And you can see that the planet and its ring system is tiny. Here are the orbits of the various satellites. Here is Titan, which orbits at 20 Saturn radii. And then the magnetic field and the magnetosphere really extends much, much further. What we study is basically what is the dynamics and what is the configuration of this huge magnetosphere. One of the major discoveries of Cassini was the discovery that Enceladus is basically the source of a lot of water vapor coming out. This montage of various images, actually it shows that the Cassini magnetometer, the instrument that measures the magnetic field, on the first Enceladus flyby, detected a distortion of the magnetic field, which very strongly indicated that Enceladus is a source of huge amount of new plasma. On the next flyby, the ion neutral mass spectrometer, which measures individual molecules and ions, detected a huge spike of water near Enceladus. You can see that this is a good order of magnitude increase when the spacecraft passed near the southern pole. And when the imaging instrument, the camera looked, then this very famous Cassini plume was discovered. And this image shows the temperatures of the so-called tiger stripes, which are the source of these geysers on Enceladus. And this cartoon at the end shows that the southern region of Enceladus is the source of a huge plume that becomes ionized and basically provides a very large amount of plasma for the magnetosphere of Saturn. One of the biggest lessons we learned from Cassini, and this is just another nice cartoon of Saturn's magnetosphere, is that Saturn's magnetosphere is swimming in water. Enceladus is a major source of water. It's about 1,000 kilograms per second, which is quite comparable to the material ejected from Io in Jupiter's magnetosphere. The rings about an order of magnitude less, about 100 kilos. Saturn itself is even less. So the major sources are the rings and Enceladus. And this plasma source basically dominates the whole environment, the space environment of Saturn. I also would like to talk a little bit about the aurora, and some of these images Kevin showed, the hexagon and aurora on top of each other. Aurora is this bluish circle, and at Earth's aurora is a highly spectacular phenomenon that is created by energetic particles precipitating from the magnetosphere and exciting the molecules and ions in the upper atmosphere of Earth. The basic mechanism is the same at Saturn. So we learn a lot about the atmosphere and about the ionosphere by studying the aurora. In a very simple analogy, we could say that the aurora is like the old-fashioned TV screen that images the whole magnetosphere or a large part of the magnetosphere to the screen of the upper atmosphere, and there is a very strong connection between magnetospheric phenomena and magnetospheric dynamics and the aurora. And one of the major research areas which is occupying the Cassini plasma science teams is the connection of magnetospheric dynamics to what we actually observe at the aurora. So we are still working, and Fred Scarf, one of the pioneers of in situ planetary science, said that in planetary missions half the fun is just being in orbit. And it is very, very true, because most of the fun is when you make new discoveries, when you see something that is unexpected. And Cassini is full of unexpected results. Finally, I'd like to show a brief video. This basically puts the whole Cassini mission and the exploration of the planets into the solar system perspective. This year earlier, we at Michigan worked together. It's my talent for technology. You know, when I was a student in Hungary and I was in theoretical physics, my professor strictly forbade me from entering any laboratory, touching any instrument. Once I was so successful that the traffic lights went out for a few hours. So earlier this year we worked with the Hayden Planetarium with their new show. Their new show is Journey to the Stars, and it premiered sometimes early June. And they used about 3 minutes of our simulations and visualized them, showing the whole solar system from the Sun through Earth, through Saturn, to the edge of the solar system. And this shows, and it's circular because this is a planetarium show, so this is the projection to the dome. It shows the Sun, the visualization of the solar magnetic field. The blue lines are the separator surface separating the northern and southern parts of the solar system. You can see that there is a huge simulated solar storm that is propagating through the solar system, and Earth appears first. The camera is moving out, and the solar storm is interacting with the Earth's magnetosphere. Then the camera keeps moving out, and of course at Earth the solar storm will create an aurora and make the aurora quite strong. As we move out in the solar system and we encounter encounter, we leave Earth and move out 10 times further from the Sun, where Saturn is and where Cassini is orbiting Saturn. We will see that Saturn, compared to the solar system, is also a tiny object. Saturn's magnetosphere, which is many million times larger than the planet, encompasses the planet and the ring system, and the solar storm will also create aurora at Saturn, and this is one of the most interesting dynamic phenomena. And after that, of course, the camera and the show moves out to the edge of the solar system. And at the edge of the solar system, nice phone. At the edge of the solar system, the interstellar medium interacts with the solar system, and this is where the so-called termination shock is located. That is the end of the supersonic solar wind. And Voyager, just a few years ago, crossed the outer edge of the solar system, the termination shock, and the Voyager now is basically outside the solar system, broadcasting its information back to Earth. And when you move even further out, you will see the whole bubble of the solar system as it is inserted into the galactic medium. So when you are dealing with magnetospheres, the interplanetary and interstellar medium, you really need to put this whole into a global context. Nothing is isolated. Everything is interacting with so many other things. And I'd like to finish with this, that Saturn's magnetosphere is huge, the solar system is even larger, and of course it's all connected to the galaxy and the universe.
When we talk to young people, a lot of times you've heard the story that Saturn's density, which is lower than water, if you could have a bathtub large enough, Saturn would float. So what I've learned tonight is that, in fact, Saturn is in a bathtub of water, which is very exciting. Fourth, we have Amanda Hendricks, who is speaking about the moons, and my apologies again. I think I just can't believe that one person could actually summarize Saturn's moons in 7 minutes. So here to do the impossible.
I have 7 minutes now to talk about 61 moons. So we'll have to go fast. I'm actually just going to talk about some of the highlights here. And 61 is a lot of moons to have, which is pretty crazy, I think. And that might not even be the latest number, because it seems like it's increasing all the time as new moons get discovered. But let me see here. Actually, can I use this? Okay, I'm going to use this instead. Okay. Okay, so here's Mimas, which is the innermost of Saturn's main moons and looks eerily like the Death Star of Star Wars. Tethys also has a Death Star-esque quality to it, because both of these moons are dominated by giant craters. Herschel on Mimas and Odysseus on Tethys. And then Dione is kind of the next one out, a little bigger. I should say that Mimas and Tethys are quite small on our scale of moon, because they're about the 10th of the size of our Earth's moon. Dione is a little bit bigger and is characterized mainly by these wispy streaks here, which are actually a series of cracks on the surface, and they're brighter because they're fresher water ice is exposed there. And I should also say that all of these moons are dominated by water ice on their surfaces and throughout their interior. And this is kind of expected for this part of the solar system. Water ice is plentiful. When we start to see liquid water and water vapor is where things get more surprising. Rhea is a pretty heavily cratered, the largest of the inner satellites, and interesting in its own right because it also exhibits wispy terrain like Dione. And at some point in their past, Rhea and Dione probably underwent some sort of tectonic activity.
And then there's Hyperion, a little farther out in the system, looks like a spongy potato, and is in fact very porous, which contributes to its appearance, and it's also reddish, which is a little bit different from the rest of the moons. And one of my favorites, Iapetus, which is the two-faced moon. One hemisphere is very, very dark, and one hemisphere is very bright, and so it's very bizarre. And I will come back to Iapetus in a second. But first we'll talk a little bit about some of the small moons, just to give you a taste. Telesto, Epimetheus, Helene, Janus, Prometheus, and Pandora. These are some of the innermost moons. Most of them are associated with rings that Linda may have mentioned already. Prometheus and Pandora, for instance, sort of shepherd that outermost F ring that's very thin that Linda talked about, and they're very small. Telesto is only about 16 miles across. Prometheus and Pandora are only about 50 miles across. So there's a very wide range of sizes. And then there's a whole slew of moons way in the outer part of the system. And these are more readily observed and discovered by actually ground-based observers. And they're very small, irregular, and have irregular orbits too. They might rotate in a prograde sense. So back to Iapetus, one of my favorites. I said it has one hemisphere that's very dark and one that's very bright. So this is obviously the dark hemisphere. And this is kind of the North Pole, which is actually bright. And the South Pole is kind of bright too. And this continues to be a mystery to a certain extent. So we have some ideas of the processes that are happening, that there might be a dust source of dark material that's actually coating this hemisphere here and darkening it. But we also think that the process of thermal segregation, so the movement of volatiles and water ice on the surface from warm regions to cold regions, is very important too. But we can see that Iapetus is a very old surface. It's very heavily cratered, and there are these giant craters that are present here too. And one of the very curious things in the entire Saturn system, as you may have noticed, is this ridge, which follows the equator, and it almost goes all the way around. This ridge, it's like a seam, and it makes Iapetus actually even look like a walnut. It's very bizarre, and it's about maybe 12 miles wide at some points and about 8 miles high. So it's really abrupt, and we don't really understand the formation mechanism for that just yet. So the one satellite that I haven't mentioned yet, the biggie, but it's small, is Enceladus. And this was our view of Enceladus back in the Voyager days in the early 80s. It looks innocuous enough, doesn't look like anything too much is going on there. But there's a couple of things that were interesting, and that is that we knew that it was very bright, and it reflects nearly 100% of the light that hits it, which is interesting, and I'll tell you why. But if you think about it, that's very, very bright, because our moon, I think, is pretty bright, and it only reflects about 10% of the light. So if you think about something reflecting 100% of the light, that is bright. And it's water ice, so like snow, it's very bright. But the other curious thing that we knew early on about Enceladus is that it isn't very cratered. And you can see that, for instance, in this region here, there's very few craters, and there's even sort of this folded terrain that's interesting. But if a body in the solar system is not very cratered, and especially if it's also very bright, then that tells us that it's curious, because generally bodies, moons, even planets, as they evolve and age, will tend to accumulate craters and accumulate dark material. Meteoritic bombardment and so forth will create craters and add dark material. So things tend to get darker and more cratered. And so we look at a body like our moon, and it's pretty dark and heavily cratered, and it's geologically very old. But this was a clue that Enceladus is geologically young and perhaps currently active. And sure enough, Cassini discovered geologic activity on Enceladus in, 2005, but this actually came, the images actually came a bit later. Thomas sort of alluded to some of the measurements that were made that actually discovered the activity. And this is one of the exciting things about Cassini, that there's 12 instruments on board, and nearly all of them contributed some little piece to this whole discovery of activity on Enceladus. So that was pretty neat. So anyway, there's a giant plume at the south pole of Enceladus, and it's made up of these individual jets that you can see that eject water vapor and water ice grains and some other vapors such as ammonia and hydrocarbons out from the interior of the body. So I said it's centered on the South Pole. The South Pole is about right here, and when you look at the surface like this, it does look interesting. So it's got these what so-called tiger stripes. This is kind of an enhanced color image here. And it turns out that, that's really where all the action is. There's fractures on the surface that are actually hot. So this is from the long wavelength infrared camera on Cassini that is showing that, we knew going into this from the earlier flybys that the South Pole had a hot spot, but now we actually know that the heat is actually coming from those fractures. And we also know that the jet sources are located along these hot fractures. So we still have questions. We still don't know exactly why there would be this much heat and what the exact source of the plume is. And we have a pretty good idea that we need some amount of liquid water under the surface, but how that water could be kept liquid at such a tiny body and so far out in the solar system where everything should just be frozen. It's really quite a good mystery. So the plume extends very high. We've seen this image before. A lot of the material falls back onto the surface, but some of it is lost and ejected out into the system. And so, I'll end actually with this image right here that shows the effect of Enceladus and its activity. It actually creates the E-ring that Linda and I think Kevin showed very nice images of. That is a giant ring in the system, and it actually plays an important role for adding water into the system. That makes Cassini and Saturn swim in the system, and for creating an environment in which the other moons orbit that affects their surface composition as well, and other effects too. So here's little Enceladus just ejecting material away and just active as can be, and creating this broad E-ring. So it's a fascinating object with far-reaching effects. Thank you.
And lastly, to talk about the king of the moons, if I can call it that, of Saturn. Here we are. See if I can read this one here. Is Jonathan Mooney.
Okay, thank you, Laura. By the way, I like that picture you had of me in the introduction. I was struck by how much Amanda and I, we are, you don't know this, but we are identical twins.
I didn't say that, so in case you want to know what he looks like,
That's
this is what
right,
he
this
looks
is
like.
right. We were separated at birth. It's past my bedtime. How many people are up past their bedtime at this point? That's how I feel. But I have a news flash for all of you, in fact. Someone remembers the summer of 2008. News flashes. Yeah? It's actually good. And that news flash is that Titan should not be thought of as a moon of Saturn. It really needs to be thought of as its own world. It really is a world. And this is something that Cassini and Huygens have shown us. One of the major discoveries of this mission is, in spite of the fact that Titan orbits Saturn, it really, in all ways, is very much like a planet. It's the size of a planet. It's bigger than the planet Mercury. It has a dense atmosphere. That atmosphere was actually discovered almost 60 years ago from telescopes on the Earth. And in fact, in this picture, we very rarely get to see pictures of planetary objects with stars behind them. This is one of the reasons why some of our friends absolutely insist that all these pictures have been faked, because there are no stars in the back. But in fact, what you have to recognize is when the sun is shining on a planet or a moon or whatever, that light is so bright that you can't capture the stars behind it. Even in the vacuum of space, the contrast is just too great. So Titan is shown here in this image being illuminated by Saturn and by Saturn's rings. And it's in the shadow, it's in eclipse, it's in nighttime. And so we can see the stars behind it. And it's a long exposure, so those stars are smeared a little bit. But this is a world that happens to be around another world, namely Saturn. So 3 centuries ago, Titan was discovered. Much about it was not known. The atmosphere was discovered 50 years ago. Voyager 1 flew by in 1980 and found that this atmosphere is very dense. In fact, at the surface of Titan, the air is 4 times denser than the air in this room. Believe it or not, after all these talks, the air may seem very dense here, but 4 times denser than the air in this room, and yet Titan is not the size of the Earth, it's only the size of Mercury, so its gravity is about that of our own moon. It holds an atmosphere because it's so far from the sun that everything is cold. It's minus 290 Fahrenheit at the surface, and that allows Titan to hold on to an atmosphere, whereas bodies about the same size, for example Mercury, could not do that because Mercury is just too close to the sun. But the surface of Titan has been a mystery, and it was finally revealed in a way that is truly spectacular. One of the things about this mission is that Cassini has the capability to smell and taste as well as to see things. But it also actually deployed a very, very heavy and complex probe called Huygens, which was built by the European Space Agency, which actually descended to the surface of Titan. And it carried its own symphonic orchestra with it, by the European Space Agency. And after a trip of several weeks, in January of 2005, it plunged at hypersonic speed into the atmosphere of Titan, landed on the surface, took images, made chemical measurements, and boy, that went by fast. Doesn't do that on my computer. Okay, well that's good. So if you put together all of the images that the Huygens probe took as it parachuted through the atmosphere, you see this very strange, surreal landscape. And this is actually a mosaic of images that average out to an altitude of between 30 and 40,000 feet. So this is really a jetliner view of the region of Titan where the Huygens probe landed. The probe actually landed just about in here. These are dune fields in the background, about 15 miles away. And yes, the air is very, very hazy and cloudy. The dune fields are not dunes of sand, they're dunes of organic material. We know that from instruments on the Cassini orbiter. This is a hill of ice that's about 1,000 feet high, not a very impressive mountain, but there aren't very many mountains on Titan. And then there are these interesting landforms that are actually debris fields of material that has come down from these hills. And in fact, with images that are higher resolution from the camera on the Huygens probe, we see fracture systems that seem to be filled with some dark material. We see these valley networks that are small. This is an area a couple of miles across. And then down at the landing site, these rounded pebbles. When you put all of these things together, what you realize is that this landscape has been modified by flowing liquid. Now at minus 290 Fahrenheit, it's not going to be liquid water, right? Because water freezes at 32 Fahrenheit into the instrument, and there's even a dewdrop of methane that formed on the probe. So methane is carving these channels, welling up through these fractures, and through these river systems, tumbling and smoothing these rocks, probably rocks of water ice, down by the landing site. And so whereas we have a water hydrologic cycle on the Earth, there's a methane hydrologic cycle on Titan. Now where's all this methane coming from? Well, we don't know, but one of the other important discoveries by Cassini, now from the orbiter, was of a series of lakes at the South Pole and the North Pole of Titan. This is the North Pole of Titan. The background image is the camera system on Cassini. The foreground images are strips from a radar system, which also emphasize the international aspect of this mission, because the radar is a joint U.S.-Italian experiment that was built That's my alarm. It's time to go to bed. Thank you. And so what the radar system, which was built by Ozzy in Italy and JPL here in the US, revealed were these dark areas, very, very dark, very smooth, in a landscape which looks like it's been carved again by channels. And all of the evidence that we have from the instruments on Cassini is that these are filled with liquid, that they are basins filled with liquid, the dark areas. The biggest one in fact is larger than the Caspian Sea on the Earth. The smaller ones you see here are a few miles across. And unfortunately we can't go and touch them and taste them. The Huygens probe ended up at the equator. These are at the poles. But we're getting more and more data from Cassini on these lakes and seas. Here's one that's in the southern hemisphere called Ontario Lacus, which is Latin for Lake Ontario. It's just about the size of Lake Ontario, about 170 miles long. Here's an image from the Cassini camera in 2004. Now watch this image because I'm going to switch to a radar image that was taken in 2009, 5 years later. And not only do you see a bit more clarity with the radar because it penetrates the haze, but you also notice that the lake has gotten smaller. Now, I think, and many other of my colleagues think, this is not just an instrumental effect. The lake really has gotten smaller. And why has it gotten smaller? Well, in Southern California, we're used to lakes drying up, right? We do that all the time, so nothing special. In this case, the southern hemisphere has been in sunlight by the time this picture was taken for about almost half a Titan orbit, 14 years. It's been through summer. Saturn, as it orbits the sun, has a year that's about 29.5 years long. So that's the year on Titan. Each season then is a little bit more than 7 years long. Cassini arrived in the summer, and from 2004 to 2009, the sun has been shining on these lakes, and so we expect they should be evaporating. And the amount of evaporation that one expects over 5 years is just about right to cause the shrinkage that we see in this lake. In fact, we know what the topographic profile of this lake is because there are altimetry measurements from Cassini. So putting all that together, the shrinkage of this lake is consistent with it being methane, and that methane is being transported from the South Pole to the North Pole. Now that's not all that's in this lake. There's a sister molecule to methane, which is a simple organic molecule made of 4 hydrogens and 1 carbon. Its sister molecule is called ethane, 2 carbons and 6 hydrogens. It mixes with methane but doesn't evaporate the way that methane does. It gets left behind. And ethane was actually directly detected by one of the Cassini instruments, by what's called the VIM spectrometer, in Lake Ontario. So these lakes contain 2 kinds of liquids, methane and ethane. It would be like the lakes and oceans on the Earth containing 2 kinds of water, evaporating water and still water. But we don't actually have that. There's no real analogy for that on the Earth. So Titan has lakes, it has rivers, it has clouds, there's evidence for rain. Not only then is Titan one of 4 solid worlds with dense atmospheres, along with Venus, Mars, and Earth, but it's one of only 2 solid bodies in the solar system which have open bodies of liquid on their surfaces and therefore have a hydrologic cycle. And the Earth is the other one. And so for that reason, we really have to think of Titan as a complete and dynamic world. So what is the future for studying this hydrologic system? Well, we are now, as you've heard, at this magic point called equinox, which means equal night, equal day and night on Saturn and Titan. That means that the sun has set over the southern polar region, and the sun is now beginning to appear over the horizon in the north polar region, where you saw those radar images. And now the hope is we can begin to see the lakes, which are actually bigger in the northern hemisphere region, themselves begin to evaporate as we move from equinox towards solstice over this long 7-year period of what is northern hemisphere spring. And so Cassini will undoubtedly show us surprising changes, weather, and so on in the lakes region in the north. We'll learn something about how climate works on this world, a very exotic world where rivers of methane run down to a sunless sea. As alien as any world you could imagine in Star Trek or Star Wars, certainly. So a wonderful place to visit and a wonderful place to explore. Well, wear a heavy coat.